Alrighty, so today's video is all about directing effects and what's going to happen if we have multiple substituent groups already on the ring before we complete an EAS reaction. So we know that for an EAS reaction, if we have different groups coming off, that these groups are actually going to affect where the product goes. So we're going to look at that first, and then we're going to look at if we have multiple groups, then where's the product going to be? Say we have something that's ortho-para-directing and we also have something that's meta-directing. Well, where's our product going to go? So we're going to analyze all of that today in this video. So for the first thing, we're just going to start by looking at all of the groups and trying to figure out whether they're activating or deactivating, and also trying to come up with a way that we don't just memorize each of these, but that we try to understand how we can look at any group, even if we don't know that group, and figure out whether it should be activating or deactivating. So some examples for activating groups are OH, OR, NH2, NR2, and R groups. So something that the first four have in common is that each of the molecules that are actually going to be attaching to the ring have a lone pair that they can donate. And they also have a partial negative charge on that atom that's attached to the ring. R groups are also activating because they can donate some electron density to the ring, or pull away some electron density from the ring, I should say. So if we were to draw out all of these groups on a ring ready for an EAS reaction, we'll see that this OH is pulling away some electron density. It's got a partial negative charge, and it's got a lone pair of electrons. So this is an activating group that we have here. And now a deactivating group, a lot of these molecules actually have carbonyl compounds on them, and the reason is because we know that the carbon that's attached to the carbonyl will have a partial positive charge. Okay, so now we can go through, we can draw in all these partial positive charges, and this will also have a partial positive charge. So for each of these deactivating groups, all of them have a partial positive charge that's directly attached to the ring. So we could draw out this one, and we'll see it's a partial positive charge attached to the ring there. And then last but not least is the halogens, which kind of have their own weird thing that we'll go into later. But they are deactivating, but because they have lone pairs to donate, they are definitely going to be ortho-para directors. So we know that, okay, to sum it up here, we know that if it is a partial positive or a lone pair, it'll be ortho-para directing. And this is on the carbon that's attached to the ring. And then if it's partial positive on the carbon attached to ring, it is deactivating. And then halogens are deactivating ortho-para directing. But really, if you just remember that it's ortho-para directing, that's all you really need to know for the understanding of an exam. Okay, so next thing is I'm going to briefly run through a mechanism just for ortho-para directing, and then from there you should be able to do the mechanism on your own to try to understand it for meta-directors as well. Okay, so let's say we're doing an EAS reaction, and for the ease of this example, I'm just going to write the super electrophile as E+. So let's say we come here and start our EAS reaction. Our electrophile goes here, and we'll have a full positive charge on that carbon right there. And so from here we can actually say, okay, well, every 2 is where we're actually going to have that full positive charge on the carbon. So we'll see that there's going to be a full positive charge on the OH, and we can draw that out next. So we can draw this bond will come over here. And then we'll have our positive charge right there. Okay, and this allows us to make a bonus resonance structure where we actually take one of the lone pairs from the OH, bring it down to make a pi bond, and then the positive charge will actually end up on the OH. And what's so great about this is if you remember about how to make the most stable resonance structure is for everything to have a full octet. And here you'll see that oxygen has a full octet and all the carbons have a full octet. So this is the most stable resonance structure we can possibly get, which is why things that have a partial negative charge or a lone pair to donate are going to be orthopara activators, because they're going to activate this reaction because this is super stable, right? And so if we were to do this for meta activators or meta deactivators, we would see that this here is still possible if we were to switch this out with a deactivating group. We would see that we could get a positive charge on that carbon that's right next to this partial positive charge, and we know that opposites attract, right? So if we have a partial negative charge, we want a partial positive charge right next to it. That's more stable. But having a partial positive charge next to a full positive charge is very unstable. So this is why these deactivators do not make the orthopara products, right? And so we also can, by the same logic, we can say that things that are orthopara activators, if we had in the meta position, we wouldn't make this bonus resonance if it was in meta, and so that's not as stable. And then similarly, if we were to take this same thing right here and just change it out with a fluorine, the reason that fluorines and halogens in general are deactivating is because this bonus resonance structure is still possible because it has a lone pair to donate. But having a full positive charge on a fluorine or a halogen that's super electronegative is not stable. So that's why that one has a full positive charge there. And the last thing that we're going to look at real fast is what to do if you have multiple substituent groups on the ring. Okay, so if we have multiple substituent groups on the ring, there's 2 rules. So the first one is that orthopara directors always beat meta directors. So, for example, if we had an R group, which is a pretty not strong activator, and we also had an NO2 group, and we did an EAS reaction. Let's say we did just bromination. Well, our products would be one having the bromine para to the R group, and the other would be having the bromine ortho to the R group. But one option would not be having the bromine meta to the NO2 group, because the orthopara directors are always going to be meta directors. And our second rule to remember is that strong activators beat weak activators. So if we had an OH group, which is a really strong activator, and we also had a bromine group, was a pretty weak activator, and we were doing the same reaction, adding a bromine group, our product will end up being, or that should be an OH. And here's the bromine, that's para, to the OH, and the other product would have the bromine being ortho to the OH. So as you can see, the new bromine is not going to be ortho or para to the bromine because the OH is a strong activator. So I hope this video helped. I got a lot of this information from Organic Chemistry as a Second Language, so if you're having any difficulty with this, I would definitely check out this section and read it. They have a lot of really helpful practice problems that I would definitely recommend doing.